Applying a non-zero net torque causes a change in the rotational motion of an object. And remember, when we say a change in rotational motion, we are meaning a change in angular velocity, or what would be an acceleration. So we're going to say our torque net is going to cause a net angular acceleration. Now, when we did force equals mass times acceleration, mass was essentially our proportionality constant in there. Here, it is going to be moment of inertia of the system that you're applying the force to. Now, don't forget, as we learned at the beginning of the chapter, torque net is equal to force perpendicular times the lever arm. And remember, you need to do force times the lever arm distance for each individual force that is acting on the system. So remember, there's two halves to this equation. One that allows you to calculate the torque, and then one allows you to see what that calculated torque does to the system, or the change in motion that it causes. Now, it is possible to have a scenario where you have a torque that is non-zero, but a force net that is zero. So let me demonstrate that for you. So imagine you have, instead of a doorknob, but sort of like a circular door handle you might see like on a submarine. So you have a post that comes out, and then there's a circular sort of piece of metal, and it's attached by an even number of spokes. So this is nice and perfect and symmetric, unlike my drawing. And you apply a force along the edge, so force 1 and force 2. And we're going to say force 1 is equal to force 2. Now, technically speaking, right here on our rotation point, there is a force normal and force of gravity that are essentially keeping the door handle sitting there. So those are actually at the rotation point, and I'll explain why the force of gravity is applied there later on in the lecture videos. But they are there, and since they're at the rotation point, the distance from the rotation point is 0, so force times 0 is 0, so we're not going to worry about those. So as I said, here we have a force normal, force of gravity. Those are equal and opposite because it's not moving up and down. And I just stated that force 1 and force 2 are equal to each other, and this one is up, this one is down, so they're equal and opposite to each other. So if you add them together, you're going to get 0. So the net force acting on our door handle here is 0. But this force is up, so our lever arm is here. So we're going around like this. This is counterclockwise, which is positive. Our lever arm here is the same, and happens to be R1 equals R2 because it's a circle. And our force is going to push around like this, which is also counterclockwise. So it's also going to be positive. So you're actually just going to add the two torques together. They're not equal and opposite to each other because they're both going counterclockwise. So we have a scenario here where the net force is 0, but the net torque is not 0, and we get the object to rotate, but the object is not moving up and down or left and right.